Okay, so here's an example of that, the volts per turn of a transformer. So 120 volts and 240 turns. So I determine, based off the information given, there's 120 turns, 120 volts, 240 turns. I can figure out my volts per turn ratio. So 120 volts over 240 turns. So that's zero 0.5 volts for every one turn on the primary. Okay. Calculate the number of turns in a transformer winding. So we just did this, sorry, 120 divided by 240, 240 turns. So this is my volts per turn. Okay. So that is equal to 0 0.5 volts for every one turn. Now on the secondary, I've got 32 volts. Okay. So I know that my V secondary would be equal to my number of turns on my secondary times my volts per turn ratio. So if I want to figure out how many turns, I'm going to take my volts, figure out number of turns on the secondary. I'm going to take my voltage on my secondary and divide it by my volts per turn ratio. So let's have a look here. My secondary voltage is 32 volts. I'm going to divide that by 0 0.5 volts per turn. And that should come to 64 volts. So 32 divided by 0.5 is 64 volts. Or 64 turns, sorry. 64 turns. We're looking for turns, not volts. Okay. So we can use these ratios and still figure it out uh, however we would like to. I guess this is a good way to remember it. The voltage equals number of turns times the volts per turn. And then you can transpose that. Just treat this as a unit, right? Number of turns times volts per turn. Erase all ink on a slide. So 0.5 volt per turn, just review. So 32 divided by 0.5, 32 volts divided by 0.5 volts per turn gives us 64 turns, number of turns. All right, on this one, calculate the number of turns in the secondary winding. Same concept. If we can review here, and we can do a couple of methods with this. So I didn't give you a method to use here, but we can use two different methods based off what we've learned so far. So we are going to go on the first one. Let's go with the voltage ratio. So we know the voltage on the primary is to voltage on the secondary is equal to the same ratio as number of turns on the primary to number of turns on the secondary. So if I can figure out this ratio, then I know this one. So let's go ahead. 120 to 24. And if we express that in lowest terms, we would get that it's a 5-to-1 transformer. So 120 divided by 24 is 5. 24 divided by 24 is 1. And those are the same ratios. So if I look at my turns here, 360, and my unknown is the secondary turns. That's what I want to figure out. For every 5 turns on the primary, we've only got 1 on the secondary. So if I take 360 turns and I divide that by 5, so 360 divided by 5 is 72 turns on the secondary. So there's one method we could use. What's the other method? We could use the volts per turn method. So if I've got 120, we know that the volts per turn on the primary is the same as the secondary. So I use the primary values, 120, divide by 360 volts, or turns, sorry. So 120 divide by 360. So we got 0.333 volts per turn. It's repeating forever. So I'm just going to cut it off at 3 decimal places. And if I want to figure out the number of turns, well, I'm going to write out that formula so we can remember it. Voltage of the secondary would be equal to the number of turns on the secondary times what is the volts induced for every turn. I want to find the secondary turns, so N secondary would be equal to my voltage of my secondary divided by my volts per turn ratio. So 24 volts divided by 0.333 volts per turn is 24 divided by alpha answer 72. 72 turns on the secondary. So a couple different ways. There's always different ways to do this. Sometimes you're going to get questions that force you to use volts per turn. Sometimes you'll get them that will force you to use volts per turn ratio. Sometimes you'll get them that you'll use the transformer ratio. All right, let's go to our next slide here. Okay. Pen. And erase all ink. There we go. Okay. We're going to look at this a little closer. Tap transformers, I'm going to have a whole nother video on this, but a quick explanation. This is a transformer with the secondary tapped. So just going to make sure my pen's working. So we have one winding on the primary here, and it's got 600 turns. And so we take 120 volts and we split it up amongst 600 turns. That's where we establish our volts per turn. So that'd be 120 over 600. Oh, keep on doing that. 600 turns. Okay. Now, so what does that come to? 120 over 600. 0.2 volts for every one turn. So that's where it's established right there. How many volts per turn? Now in the secondary, if we look at this, this is called a multi-tap transformer. So we have the secondary here. Here's our winding. Goes all the way from one end to the other. But what they do is they take out a tap partway through. So there's only so many volts induced per turn. So we take off a tap a little bit earlier, and then maybe one a little bit later, one a bit later. So we end up getting a multi-tap secondary. That means that we can produce a variety of voltages. So in this case, a 12 volt, 16 volt, or 24 volt output we can have. We have a choice. Just depends which wire we want to connect up. So let's figure out on this example to use this tap secondary to have a look and say, well, how many turns are if we go and use the 12 volt setting here? So on the 12 volt setting, I take 12 volts, I divide it by 0.2 volts per turn. That was established on the primary. So 12 divided by 0.2, 60 turns. If I want the 16 volt setting, how much from here to here? Well, 16 divided by 0.2, 80 turns total. And the 24 volt divided by 0.2. 24 divided by 0.2. 120 turns. So we have 120 turns here, we have 80 turns here, and we have 60 from here to here. So as we add turns, the voltage goes up on the secondary. As we take away turns, the voltage would go down. Anyway, so that's that concept where we can see volts per turn on those multi-tap transformers. Just going to erase all ink on the slide.